Welcome back, Nemeth students. This week we're diving deeper into signs of operation and signs of comparison with the Nemeth code. With signs of operation, I want to remind you first that whenever we braille an equation in Nemeth, the signs of operation have no spaces around them. So if you look at an example like 4 plus 3, there's no spaces on either side of the plus sign. This week, we're going to add on some of the more advanced symbols like plus or minus to that, but they're still going to work the same way. No spaces next to them. They touch what they act on. Special signs of operation may relate to their meaning. So here I've got a couple examples for you. After just the plus sign, I've got a union. So the union of A and B, that place where both of them are. Or a logical sum, right? So the M and the logical sum of N. So adding those two things together, you'll see that the logical sum is two cells. It's got a prefix and then a root. And that root is the plus sign because in some way, the math of that logic equation connects to the math of just adding to begin with. It's a little more advanced, but they're still related. So it's built on the same shapes. We just add prefix, something in that .456 category to change the meaning, the type of addition that we're doing. This is true even though the print symbol, if you look at my translation bar at the bottom, the print symbol for a union or for a logical sum doesn't really look anything like a plus sign. In Nemeth, because the meanings are related, the Braille will be related. And so that's just kind of wonderfully elegant and one of the special treats about how Nemeth works. This week you will learn to write a lot of the different logic functions. It's okay if you never took logic as a math class. The Braille just follows the print, so you'll be able to just follow along and insert the next symbol. Even if you wouldn't really know how to solve that equation, that's totally fine. We're just learning the Braille at this time anyway. I have a couple more examples along that line. So 9 divided by 3, you see our 9, our regular division symbol, the one with the line and the 2 dots, and then the 3, no numeric indicator needed for the 3 because our sign of operation does not cancel numeric mode. There are other things related to division, like a forward slash. If you think of writing 1/3 kind of linearly with a slash in it, you can do that. Or our actual fraction line, because fractions really are always dividing the numerator by the denominator. So even our fraction line is related to that division sign. As we get more advanced in math, we get some more signs. Probably, I think the most common complex sign of operation is the plus or minus sign. Sometimes in math, we don't know if something is positive or negative, and it actually could be either one. And so there's a symbol for that called plus or minus. And it gets into kind of the reasons that we need to start adding some unique indicators in Braille. Remember, in Braille, an indicator is something that has no print equivalent. It changes the meaning of things, but you don't actually write that symbol in print. So this is an example of a square root. And the translation line is not indicating that it's a root right now, so I just wrote it out. But this symbol means start the root. I'm taking the square root of 9, and this symbol just means end the root. So the square root of 9 equals, you probably think 3, right? But if you remember back to kind of the more advanced math classes you took, you might remember at some point learning that the square root of a number is actually whatever its root is, but it's the plus or minus of that root. And that's because 3 times 3 does equal 9, but -3 times -3 also equals 9 because 2 negatives multiplied together equal a positive. So when we take the square root of something, we don't know if our answer should be positive or should be negative. In reality, the answer is both at the same time. So math has a symbol for that. It's the plus or minus symbol. You can see it down in the translated line in front of the 3, plus or minus. So if I say the square root of 9 equals plus or minus 3 in math, that's pretty common. To Braille it, there is a Braille symbol for that plus or minus symbol. It's made up of a plus symbol and a minus symbol, just stuck together. So plus or minus 3. that's a sign of operation you'll learn this week. Like other signs of operation, sets numeric mode, it needs to be unspaced from the things it operates on. All of those things for signs of operation still hold true. This week, you'll start to learn about the multi-purpose indicator. Multi-purpose indicator can be used when there are unrelated signs of operation touching each other to show that they're separate. So if instead of writing plus or minus 3 and wanting that plus minus, I actually just wanted to write a plus sign and then a minus sign, or maybe more commonly a minus sign and then a minus sign. 9 equals 6 minus a negative 3, because when you take away a negative, you add a positive. So to separate those two symbols, the one that is minus I'm taking away and the one that is negative, I put in between them a .5. The .5 multi-purpose indicator just lets me know the next cell is happening on the baseline again. It's not stacked. It's not part of a compound shape. It's just the next thing on the baseline. It's a way for a Braille reader to know that two symbols are separate and not really run together, and that lets us build all of those complex indicators and shapes that we do want to build together efficiently. This multi-purpose indicator, this .5, also is used to end superscripts and subscripts. It can be used in relation to where bar over other kind of modifiers start. So sometimes we call it a baseline indicator. Its technical name is the multi-purpose indicator. What's important is that it's a .5. You write it with your right hand. Keep it a .5. Don't flip it around. It's too important to flip it backwards. It means other things in other places. So don't make it a number 1. Leave it as .5. It's the multi-purpose indicator. Because it's introduced here, this might also be where you want to go view the upper elementary math lecture. If you enjoy thinking about math terms kind of grouped into the age levels where kids learn them and are liking that series, this might be a good time to go watch kind of that 3rd grade through 5th grade content. Then we get into signs of comparison. There's a way to Braille each sign of comparison that exists in print, even the weird ones you don't use every day. Just remember, if it's a sign of comparison, if it compares how the first half of the equation relates to the second half of the equation, rather than operating on one number with another, signs of comparison get a space on each side of them. There's a space before and a space after. Doesn't matter how many cells long the sign of comparison is or how complicated the sign of comparison is, there's still a space before the whole thing, a space after the whole thing. The most common ones sort of follow the structure of an equal sign. So if I had an equation, I'll put the number first. If I said 5 equals x, our equal sign shows both sides are the same size. We always write it right hand then left hand across 2 cells. The more rare ones might have longer prefixes and suffixes, but this is kind of our base shape for comparing two things that are equal. Then if we do less than, we'll make the side that's smaller, literally smaller. It'll be just a .5 if it's less than. If it's greater than, we'll make the first side bigger and leave the side that's smaller, smaller again, and so that time it'll be a .2. Our greater than and equals, if you learned the alligator eats the big number, totally still works in Nemeth, which is great. So that same kind of mnemonic that a teacher might be using in a gen ed class is going to actually make sense to your blind kids if they're writing in Nemeth. We can modify these just like we built plus minus by putting two symbols together. We can modify less than and greater than the same way. So a common one is for something to be less than or equal to or greater than or equal to. Those use a standard shape formation in Nemeth that we use whenever we add a line to a shape. You'll see it again later when we do line segments and you put the line over the letters that name the line segment. But if I wanted to make x less than 9, right, I could do x is less than 9, we already did, or less than or equal to. For less than or equal to, I start off with my less than, and then I add my or equal to with a bar. A bar is dots 156. And so I could say it's less than 9, or less than or equal to 9. I could make the same structure and do greater than or equal to, and you see when I add that bar how it just adds the or equal to in my translation line to 9. Do that same thing. And there are other forms. There are really rare forms of this, like having multiple bars or having the bar be on top, for example. If I wanted to write the bar on top, you can. If that's what it has in the print, I would just do the bar first and then the greater than sign. And my computer apparently is unable to recognize that symbol, not because that's not the right symbol in Nemeth, just because it's so rarely used that nobody bothered to program the computer to know that's what it was. So as a Braille reader, it's really easy for me to recognize that this is the same as the other one, just flipped on its head. The computer is not quite that smart, but that's all right. It doesn't need to know everything. You will see that bar shape again later when you learn to name things like line segments. When we're making these signs of operation and comparison, we generally put them in the order that they're read. Another common piece of the puzzle that you'll use is a tilde, which is like a little squiggle line. It's used really commonly to show that something is approximately equal to, and in approximately equal to, maybe we're comparing A is approximately equal to B. It's usually 2 tildes swiggled together. So I would do it twice, and that makes the 2 together. That is the most common form of that sign of comparison. So you see that's the one the computer knows how to recognize. If I say A is approximately equal to B, they're close enough. But I could, again, use that modifier to lots of shapes, and it would still work and still make sense to a Braille reader. If you end up with a string of signs of comparison, maybe if instead of X is less than or equal to 9, it was written in the print with a less than sign first and then an equal sign, I can't just put an equal sign after that, or in Braille, that ends up modifying and being a combined symbol. If I want them to be separate symbols, if it was actually just listed out as a string, I can always use my .5 in the middle to say one and then the other. There would be no space, but it would indicate that the list of signs of comparison are there. I see that my computer is having a moment where it thinks that it should be a Greek letter because of the spacing, but it would mean the same thing. We don't space them when we use a .5. It tells the reader to move on to the next item rather than using a space to do that. So what's the point of all of this? Why am I highlighting all of these shapes and how they're built? I respect that you may not be a math nerd. A lot of the symbols in advanced kind of calculations and signs of comparison and operations might be things you look at and go, is that an operation? I've not seen that symbol before, or I haven't seen it in a very long time. Maybe you've even never seen it, and that's okay. You don't have to be a math nerd. But I do want you to equip your blind students to be math nerds. Each component of the Braille sign, and usually the print sign too, but it's a little more convoluted in print, harder to recognize. Each component of the Braille sign has a meaning that it carries with it across the different symbols. Once you know that in a sign of comparison, .34 negates the sign, you can recognize many new symbols and their composite meaning. If you learn a new sign of comparison a future year in math class and then see it written after a .34, you'll just automatically recognize that it means not perpendicular to, if you already knew that not equal to was built that way. In Nemeth, we can read using these parts and context clues to make sense of new symbols as we come across them. It works just like phonics in reading regular words. And that is incredibly powerful for math literacy. It's one of the major gifts of the Nemeth code. So as you teach your students symbols that come up in their math classes, when they ask you, why does this have a prefix and then a plus sign? I know you're going to look it up quick, or ask the math teacher how to read that symbol, and that's fine. You don't have to know all the math as the TBI. But lean into their question as a teachable moment. That symbol has a plus sign in it because in some way it's a related concept to addition. Happy Brailing!